Welcome to Lecture 4 of Experimental Vibration Analysis. In this lecture, we discuss statistics and random data analysis, also called stochastic process theory in mathematics. We will discuss how to apply the theory to data quality assessment as well. The content of this video is found in Chapter 4 of the book, Noise and Vibration Analysis. This lecture is divided into 3 videos, covering an introduction to statistics in the present video, then a video about hypothesis testing and testing for stationarity, and finally a video describing how to do data quality assessment. I will assume in this video and the following videos that you have studied a statistics class prior to this lecture, except for hypothesis testing, where I assume it's new for you. Therefore, I will focus on summarizing some of the most important statistical measures or properties that we typically use in vibration analysis, and I will focus on the practical use of it. Let's start by defining a random signal. A random signal, or a stochastic process x of t, can, at least loosely speaking, be seen as a function of random variables. This means that at every time t, the signal is arbitrary. This means that it cannot be predicted from previous values, nor can anything be said about its previous values from an observation of values during some time. This does not, however, mean that the random signal is totally unpredictable. As we will see, the random signals that we are interested in have some constant mean properties, such as the mean value, the RMS value, etc. Here you see an example of a random signal, an acceleration as a function of time. This could be the acceleration of a building or a bridge under wind excitation, for example. It could also be an acceleration on the wheel hub of a car or truck. As you see, it oscillates rather arbitrarily as a function of time. Stationarity is a very common and important concept. A random signal is stationary if the mean of the signal and the mean of the signal squared, etc., are all constant. Some stationary random signals are ergodic. Ergodic signals are stationary signals for which time averages equal ensemble averages. We will come to that soon. In this lecture, from now on, we will assume that we have ergodic signals and thus stationary signals. We assume additionally that all signals have zero mean. Now, the fact that we talk about stationary and assume stationary signals here does not mean that you should think that all real signals are indeed stationary. On the contrary, most of the signals we find in the field are not stationary. So stationarity is a very important thing, and that's why it's important, and we are dedicating a special video, 4B, to testing for stationarity. So we will assume signals now are stationary and ergodic. It's important that you understand the difference between ensemble and time averages. So one of the important concepts in the theory of random signals is the concept of ensembles. You see, the mathematician thinks of a stochastic process, a random signal, as a kind of nature of the signal. This process can have infinitely many realizations. Every time you observe a particular signal, you're looking at a realization of that thought process. An example of a stochastic process can be, for example, the road sound that you hear in a particular car, driving on a particular road surface at a particular speed and with particular tires, etc. Think about anything that may affect the sound. So if you take a specific car, take your own for example, and you measure the sound in your car, you will measure a realization of that process. If you have several realizations, they form an ensemble as indicated in this figure. Now, it's very important to realize that an average in stochastic process theory is thought of as an ensemble average. Thus, it's dependent of time. So the mean of the signal, which we indicate mu x of t, is the mean of the realizations x1, x2, etc. at time t. And similarly, for the standard deviation, we will define all these measures later, but I assume that you know them. This is, of course, impossible to obtain experimentally. We would need infinitely many, or at least quite a few, cars driving simultaneously on that same road. That would get very crowded. But luckily, as we said earlier, if the signal is ergodic, and therefore also stationary, then we can take one realization and make the average overall time values instead of ensemble averages. This is, of course, experimentally possible. And this is, in practice, what we always do. But you should keep in mind that this is only allowed for ergodic signals. So ergodic means that the time average and the ensemble average results in the same value. Now we will summarize some of the most common statistical properties just to make sure you're on track with the tools we will use. First, the expected value of a random signal is simply the theoretical mean value of the signal. That is the mean we would obtain if we had infinitely many values. Then we have an estimator of this value, mu sub x hat, where the hat means that it's an estimate. It's measured in an experiment. Sometimes we also denote this by x bar. That is the normal mean value that you're well familiar with, based on, in this case, 2n plus 1 samples. We also need some statistical error properties. So let's define these up front, because we will use them in later lectures. We have two different errors. First, we have the bias error. A bias error is a consistent difference between our estimates and the true value. Assume we have some statistical estimate phi hat, which is, for example, the mean value of our random signal. The bias error, b sub phi hat, is then the expected value of phi hat minus the true value phi. In most cases, we are not interested in the error in absolute terms. Rather, we are interested in the normalized error. The normalized bias error, epsilon sub b of phi hat, is the bias error divided by the true value. So this means that we, in essence, get the error in percent if we multiply this value by 100. The other error that occurs in estimates is the random error. We define the random error, sigma sub phi hat, as the square root of the expected value of the difference of the estimate and the true value squared. You recognize this as an RMS value of the difference between the estimates and their true values. And similarly to the bias error, we normalize the random error to obtain epsilon sub r of phi hat by dividing the random error by the true value. If we assume that we do not have a bias error, then we can use the random error, the normalized random error, to compute a 95% confidence level. We do this by taking our estimate times 1 minus 2 epsilon sub r and the estimate times 1 plus 2 epsilon sub r to obtain the lower and upper limit of the interval. Random signals are characterized by their distribution, or their probability distribution. The most common distribution is, of course, the Gaussian or normal distribution that I suppose you're well aware of. The probability distribution, which we denote uppercase P of x, is the probability that x of t is smaller than the value x. It's more common to use the probability density function, or PDF in short. This is denoted lowercase p sub x and is the derivative of the distribution function. This is the bell-shaped function that you know for the normal distribution, and we will see this later in this video. We cannot estimate the probability density function because it's a continuous function, and this is not experimental, so to speak. So instead, we use the histogram. A histogram is simply a bar diagram with, in its simplest form, the number of samples that occur in each amplitude interval in a bar diagram. So we divide the y-axis into a number of intervals, and then we count the number of samples within each interval, and we plot this in a bar graph, which we then twist around to become a plot like this. This is the histogram. To estimate the so-called sampled probability density, which means the PDF that we estimate based on a number of samples. To obtain this, we normalize the bars in the histogram by the total number of samples and then divide it by the interval length, delta x. The units of the PDF is thus 1 over the units of the measured signal. And you should particularly note that the experimental PDF, so to speak, the sample PDF here, has an x-axis with the same unit as the original signal's y-axis. Next, the statistical moments. We define the central moments m sub k of a signal as the expected value of the signal x minus its average raised to the kth power. It is called central because the average is subtracted. For us, that doesn't really matter in general because for vibration signals we suppose we have zero mean. And the moments are estimated, as indicated here, as simply the 1 over the number of values times the sum of xn minus x bar raised to the kth power. Using the moments, we can now define the standard deviation and variance, which are very common to use. Actually, we already used the standard deviation when we defined the random error earlier, but without mentioning it. The standard deviation is the square root of the expected value of x of t, minus x bar squared. This is also equal to the square root of the second moment. And if you look at a real signal, this is essentially the RMS value if the mean of the value of the signal is 0, as we assume. The variance is simply the square of the standard deviation and is related to the AC power of the signal. Next, we define the skewness. The skewness S sub x is the third moment normalized by the standard deviation to the third power. The skewness measures if the PDF of the signal is skewed, that is, the signal is not symmetric around its mean. If the skewness is not equal to 0 for a zero mean signal, then it's often an indication that there is an error in the signal. You should also note that since the calculation of the third moment keeps negative values in x of n negative, this means that, in a sense, the skewness is similar to the mean value. The difference lies in the third power. By raising all the values to 3, samples x of n with high levels, either positive or negative, are exaggerated in the averaging compared to the lower values, compared to the mean where the power in the exponent is only 1. This is essentially what differs the skewness from the mean. Next we have the kurtosis. The kurtosis is defined as the fourth moment normalized by the standard deviation to the fourth power. This is thus also a dimensionless variable. It can be shown that the kurtosis k sub x is 3 for a Gaussian signal. Since the kurtosis is based on the fourth moment, raising all values to the fourth power, they're all positive numbers. Similarly to the skewness, then, this kurtosis exaggerates high values in the signal. Therefore, the kurtosis tells if the high levels of the signal, either positive or negative, in the tails of the PDF are higher or lower than the tails for the Gaussian distribution. So, if the tails are higher than the normal distribution, then the kurtosis is larger than 3. And if the tails are under the Gaussian distribution, then the kurtosis is less than 3. Another very common statistical property is the kurtosis. The kurtosis is defined as the fourth moment normalized by the standard deviation to the fourth power. It can be shown that the kurtosis k sub x is exactly 3 for a Gaussian signal. Also, since the kurtosis is based on the fourth moment, raising all values to fourth power, it's a positive number. Similarly to the skewness, it exaggerates high values in the signal. Therefore, the kurtosis tells us about the tails in the PDF. If the tails are higher than the normal distribution, which is this black curve here, then the kurtosis is larger than 3. And if the tails of the PDF are lower than those of the normal distribution, then kurtosis is smaller than 3. The most common statistical distribution is the normal or Gaussian distribution. This is because all random signals that come from a sum of many contributions, like most signals do in vibration applications, then the sum is normally distributed, no matter how each contribution is distributed. So this is called the central limit theorem that you're probably aware of. Now, if we have a variable x which is normally distributed with mean mu and standard deviation sigma, then normally what we do is we standardize this variable to a new variable z, which is defined as x minus mu divided by sigma. This new variable z is then normal distributed with 0 mean and 1 in standard deviation, and has a PDF which is 1 over square root of 2 times e to minus zeta squared half. The PDF for z looks like this, and you may remember some key numbers for this, which are sometimes important to know. Within plus minus 1 standard deviation, or plus minus 1 on the x-axis of the normalized variable, inside the signal is inside this 1 sigma 68% of the time, whereas it's within 2 standard deviations 95% of the time. This is what we used for the 95% confidence interval before. And finally, a signal is within 3 sigma 99.7% of the time. Next, we will talk about correlation functions. These functions are very important for random signals as they characterize the signal's spectrum content. So if you want to describe the essence of a random signal, it is necessary to specify not only the PDF, the density function, but also the autocorrelation or its spectrum. But that we will discuss next lecture. So the autocorrelation of an ergodic random signal x of t is denoted R sub xx of the variable tau, the time lag. And it's defined as the expected value of x of t times x of t minus tau, a shifted version of x of t, shifted tau seconds to the right. The autocorrelation measures the similarity of x with itself, shifted tau seconds away. It's also easy to see that the autocorrelation for lag 0 is the expected value of the signal itself squared if the average of the signal is 0. And this is apparently the variance of the signal. Next, the cross-correlation functions. If you have two different random signals, x of t and y of t, the cross-correlation R sub yx of tau is the expected value of y of t times x of t minus tau. So you take the y signal, which is considered as the output typically, as we have used it before, and x of t being the input of a linear system. The average of y of t, x of t minus tau is the cross correlation. Now, one thing is, if the output signal is simply a shifted version of the input signal, so if y of t is x of t minus tau 1, then you can easily see, as is deduced in the book, that the cross correlation between these will simply be the autocorrelation of x shifted to tau 1. This is commonly used, for example, in sonars and radars, to detect when a signal sent out is coming back reflected. A few other things about correlation functions is that it's easy to see that the autocorrelation function is of course an even function. So R sub xx of minus tau equals R sub xx of plus tau. Also, if you shift the two signals x and y, the cross correlation will be mirrored. Here are a few examples of autocorrelation functions. So if you have a sine wave or any periodic sine or cosine, the autocorrelation is typically a cosine function. For white noise, which I should say is a very theoretical and unphysical type of signal, but it's very common in signal analysis literature, white noise has a theoretical autocorrelation of being a Dirac pulse, Dirac of tau. But this is unphysical. So in real life, we get the bottom plot here with band-limited noise that, or a random signal that only has a frequency content up to a maximum frequency. Then the autocorrelation function is typically a sine x over x signal that we have seen before in this course. Finally, we will just look at some of the support for statistics that you find in ABRAVIBE and in MATLAB. All the commands for statistics in ABRAVIBE starts with an A to indicate that it's an ABRAVIBE command and not to collide or not to coincide with similar commands that may be in other MATLAB toolboxes. So APDF calculates and plots the probability density function. Kurtosis computes the kurtosis, RMS computes the RMS value, Skewness for skewness, and XCore estimates correlation functions, either auto or cross correlations. And there are some simple commands in MATLAB that you can use: the mean, the STD for standard deviation, and VAR for variance. And this concludes the first video. You should now proceed to the second video for B.